I'll just introduce our speaker of today's session, Mubarak Choudhary. So he's in his third year BSc honors in mathematics, and he's from Punjab University, Chandigarh, and he will talk about Schröder Bernstein theorem. So over to you, Mubarak, and thank you.
Schroeder Schroeder Bernstein theorem. Basically, this theorem is based on cardinality of sets. That is how we can show the cardinality of two sets equal without actually counting the number of elements or other things. So, what is the hypothesis of this theorem? When we talk about finite sets, we can directly prove them equal by counting the number of elements and show them equals to the number of elements of other set. But in case of arbitrary sets, the showing this thing is very difficult. So for that, this theorem helps us a lot. So for any two arbitrary sets x and y, uh, we can show them equal. The way I am defining that, if I take a subset of a set x and show that equals to the subset of y, means equals means the show them cardinality of both of them is equals, and the remaining part from in x when we take out a, that is the cardinality of x other than a equals to the cardinality of x other than b. So by showing these two things, means this is the key point of our proof. So the hypothesis of this theorem says that, so this theorem is for arbitrary sets. That is, if we can find two maps, x f from x to y injection, that is one map, and from y to x any other one map, then we can prove that the cardinality of x equals to cardinality of y. So for this we have to prove a lemma, which is called Naster-Tarski lemma. So so the hypothesis of lemma is that for any arbitrary set x, it defines a map from power set of x to the power set of x, an increasing map. Increasing in the sense, when we talk about real numbers, increasingness is defined by inequality. But in the case of sets, here as our elements are sets, as where our parent set is the power set of x, so our elements are sets. So increasingness is defined in this way, that is, if for every a contained in b, f of a is contained in f of b. So then we'll get, then f has a fixed point. Now, as our elements are sets here, so the fixed point will be the work of fixed point will be done by a set itself. So that means there exists s subset of x such that f s equals to its image. So the proof of this theorem is constructive. So I'll try my best to prove it. So for this, we have to define a set. I am giving the proof of this lemma. So for that, we have to define a set T. I'm collecting all those C in power set of X such that C is contained in C is contained in f of C. That means when we talk about reals, C is less than equals to, if C is a real number, C is less than f of C. But now here we are talking about sets. So C is contained in f of C. Now we have defined our set T. Now I am taking S as the union of all those C in T. Means I am taking S as the union of all elements in T. So what we will get from here now? So that means every element of T is in S. So as I'm taking S as a union of all elements in T, so every element of T will be contained in S. So as our map F is increasing, the hypothesis says the map F should be increasing. So when we apply F, S is also a set and C is also a set, and S will be also contained in power set of X. As S is the union of all sets in power set of X that satisfies this property. So S will also be an element of power set of X. So when we apply uh, F here, we will get F of C is contained in F of S. So as how we have defined our T, we are taking all those C which are contained in F of C. So here every every C here, every C we are taking from T, C is contained in S, and then that F of C is contained in F of S. So also C will be contained in that F of C. So what we'll get from these two things, that for every C is seen as C contained in F of S. So we'll get S is contained in F of S as our map is increasing, and C is contained in, sorry, as all C's in S are contained in F of S. So the whole set S will contain in F of S. So as F of S itself a element of power set of X. Then when we again apply F on these two things, we'll get this, that F of S is contained in F of S. So here we are again getting the property of T, as in T we are choosing all those elements which are contained in their image. Now here F of S is contained in its image, that its image will be F of S. So will what we'll get from here, we'll get F of S is also an element of T. So as F of S is element of T, so and S is union of all elements in T, so F of S is contained in S. And from 1 and 2, what we'll get? Here S is contained in F of S, and here F of S is contained in S. So by both of these, we'll get F of S is equals to S. That we're getting a fixed point in F. So till here, we are done till here now. Now come back to our original theorem, that we are given that f is one map from x to y and g is one map from y to x. So if I take any subset of x, let's say a, and there will be some image of a, that is f of a. So as we know that this will be a bijection. The definition, what is the definition of f of a? That is all, means f of, if f is a not one map, then f from a to f of a will be a onto map. But now here in each element of f of a, there will be unique pre-image of element. For every element in f of a, there will be unique pre-image in a. So that's why then this map will be a bijection. So here from here we will get that cardinality of a is equals to cardinality of f of a. Now what is remaining? We have to prove the cardinality of this remaining part equals to the cardinality of the remaining part in ax when we take a out from x. So now for that we have defined another map. When we define f from power set of x to power set of x. So how I am defining it for any subset of x b, I am defining like this. When we take f of b, like a will be here in x, and when we apply f on it will be in y. And as we have, you can get the idea from here, as we have to show the remaining part equals to the remaining part of x when we take a out. So so as firstly we are taking element in x, then its image in g y, and then taking its complement. So as I'm changing here b, when we take b here, the f of b will be here, and when we take its complement, we'll get the remaining area. Now when we apply g on it, it will be again, as g is map one map from y to x, then it will again come something like this will be here. Then g of f of b complement will be a subset of x like this, that we don't know what that will look like. So we'll get that. Now again I am taking the complement of that whole thing, that is we'll get the area other than this f of g of f of b complement. So we'll get this area. Just this is a map defined to in such a way that we can use our lemma to prove this theorem easily. So now we have defined this map f from power set of x to power set of x. So when to apply the lemma, what should it satisfy? It should be, first of all, it should be an increasing map. So as we know, if a is contained in b, then a b complement is contained in a complement. And also if a is contained in b, f of a is contained in f of b. We all know this. So will I'll use these two things to show it increasing map. So for any a contained in b, f of a will be contained in f of b, and when we take its complement, f of b's complement contained in f of a's complement. Then again when we apply g on this, now again we have to apply the complement. Then this thing is contained in this, then the complement of this will be contained in this. What is this? This is f of a, and this is f of b. So here we'll get, when a is contained in b, f of a will be contained in f of b. So that means the map we have defined f is an increasing map. So now we'll get some fixed point in f. So let's say it s. I'm using the same notation as I used in the lemma. So there exists s is subset of x, or you can say the element of power set of x, such that f of s equals to s. Now proceeding further in our theorem. So now we are almost done with our proof. So that firstly we were taking a, any a in x. Now we'll take that s in x. So there will be some image f of s will be in y, and we know this, that this will be a bijection. That is, the cardinality of s will be equal to cardinality of f of s. Now, by using this map, as this is the fixed point for f, so the other part, remaining part here, will be equals to the remaining part here. So now we can define our map. So to show these two set equal, if we show a bijection between them, that will be good by using f and g. So I'm defining h from x to y. H of x equals f of x when x is in s, and g inverse x when x is in the part other than s in x. So that is, with the help of f we got that this s is equals to the this f of s, and with the help of capital F we are getting the this part is coming back to the part other than s. That is, the part other than f of s is coming back to the part other than s. That is, their cardinality is same. So by using that, we'll get h a bijection from x to y. So by this we can say that cardinality of x equals to cardinality of 1. So this was a proof of Schroeder-Bernstein theorem. Thank you. If anyone having any doubt,
Okay. Mubarak. All right. Uh, that was a good presentation.